to you that a cell in your body, you've got this little cell in your body, and this is how big it is. Right, that's how big it is, this many millimeters. Right, can you see that? Now, can you read that easily? Do you understand that? Because if you have to read that, it's very difficult, is it not?
It is, ma'am.
Yes,
So what they do when you've got that, or if you've got something like this, if they say you're going to send a satellite into space and it's going to have to go this many kilometers, right?
yes, ma'am.
My pen is running out, so it's, I don't know if you can see this. Right, probably not, but you'll get the idea. So if it has to go that many kilometers, you're going to look at that and you're going to think, oh my goodness, what is going on? How do I look at that? So that is the reason that we do standard form. Standard form has to have one non-zero number. So the word non-zero is coming into our vocabulary a fair bit today, right? It has to have one non-zero number before the decimal point. So if you had this horrible number here that I had shown you, and I'm going to ask you to just believe me because I'm going to count the zeros. It was 0,000,000,000,000. So there were 9 zeros, then 6, 1, 3, right? So the first non-zero number is 6. So we write 6, 1, 3 times 10. And then we count. If we had put our comma here after the 6, okay, over there, to make it 6, 1, 3. We're lying. It's not 6, 1, 3. Are you with me? So what did we do? We actually made the digits 10, 100. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places bigger. So what we have to say is we have to say to get back to this, we would have to divide by 10 times over, and you would write it like that. 6, 1, 3 times 10 to the negative 10. Okay? Now 10 to the negative 10, Jojo, you haven't done a lot of this, and Bielo's done a little bit more, means you're dividing by 10 times. So the numbers are going to be shifting 10 times smaller. All right?
Okay, ma'am.
If you have the other one, which is 579, 004, 352, 135, 13,5, I then have to write it as one non-zero digit behind the decimal point. So I'm going to write it as 5,79 times 10. And then I need to count how I'm lying again, because now I'm making millions and billions into 5. Okay? And you can't lie in maths, so you've got to adjust that. So you then have to say, how far would I be moving it, right? And you're going to count all of these positions here up to where you've put the comma. And it becomes 10 to the plus, because you've now made it smaller, it needs to get bigger. So it becomes 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we say 5,79 times 10 to the positive 10, which means our answer must get much bigger. Are you with me?
Yes, ma'am.
Yes, ma'am.
So you're going to get 2 marks for this. You get a mark for the number, and you get a mark for the power. But as I was explaining to Sinako and them yesterday, you can't write it as 5,79004352135, because it takes the whole page, right? So you're going to do what I think, Bielo, you'll remember that I used to do, which is this, right? You know that curly equal. So you're going to say is approximately equal. And you don't put straight lines, you put curly lines, like there's a little wave in your equal. And that means that your answer is approximately equal. It's not exact. All right. And you can write it like that.
Yes,
So do you understand those 2 things? They come up a lot in physics as well, and in chemistry a lot, and in biology, because certain things are very, very small, and then they have to have 10 times 10 to the power of a negative number. And some things are really big or really numerous, like if you had to talk about the number of cells in your body, okay, or the number of organisms in an ecosystem, it would be a very, very big number. Okay, so we need to be able to do that. So those two things are fairly easy. Now the third one, I did put another Zoom, but we might just refresh this one if we need to, is probability. And we're not working with simple probability anymore. So can you tell me very quickly, what is the probability that Jojo will wake up tomorrow and she'll be a man?
Ma'am, it's 0.
That's 0, right? 0. What is the probability that you'll look out of your window and there'll be a lion looking in your window?
A lion is 0. No.
It is 0. It is 0. You know, it could happen if a lion escaped from the zoo or you were living in the lion park, but the chances are so small that you make it 0. But what is the probability that it's going to be dark tonight? The sun will go down.
100%.
100%, which is 1. So probability is between 0 is less than your probability, which is less than or equal to 1. And both of the signs are and equal to, all right? So the probability is less than 0, bigger than 0, and less than 1. You can never say there's a probability of 2, because if you do, it's wrong, all right? So if it's impossible, you know that it's 0. If it's absolutely certain, you know that it's 1. And generally, it's something in between, and you use both decimals and fractions. Now, yesterday when I worked with the children, we did something like this. They said, if it's raining, let's use anybody. Let's say if it's raining, the probability that Kathy wakes up grumpy in the morning, I don't wake up grumpy. So if it's raining, who's grumpy? Well, let's just say Mr. Grouch. He wakes up in the morning. If it's raining, the probability that he's grumpy is 70%, right? Which is 0.7. That's if it's raining. If it's not raining, the probability is obviously then 0.3. If he wakes up and it's raining and there's a lot of traffic, the probability that he's going to be grumpy is going to be 0.9. And if there's no traffic, can't be real. I'm making stupid probabilities, but I'm just showing you a method, okay? So you draw a tree diagram and you have your first event. It's called an event. In this case, I will give you some notes. In this case, our first event is if he wakes up grumpy, right? So we say grumpy, and if it's cloudy, it will be 0.0%. If it's not cloudy, it will be 0.3, right? Now the second row, can you see what I've done? I've made it the same. I'm going to show you a distribution now, but last time you couldn't see anything when I looked at the Zoom. Can you see those things?
Yes, ma'am.
So this is 0.9 and then going down to 0.1. Now, can you see they're the same? Why? Because it's the same probability. It's just going to be affected by how he's woken up before. If it was cloudy, he was already grumpy. If it was not cloudy, he wasn't grumpy. All right. So there's two magic things you need to remember. And the first one is if I say it is cloudy and there is traffic. If the word is and, you multiply, right? And if the word is or, I hope you're writing notes. So I can't see you. You're always hidden when I do these Zooms. You add, right? If I didn't have to explain, I would also go blind, go hidden. So if you multiply, if it says and, you times. If it says or, you add. Are you okay with that? So if we look at this,
Yes.
and have you drawn this little tree diagram? So if I say to you, now it's cloudy and there is traffic. It's cloudy and there is traffic. You need to multiply. Okay? So you're going to say cloudy is 0.7 and there's traffic, which is 0.9. So you're going to say 0.7 multiplied by 0.9. All right, which is going to give you 0.79s are 63, so it's going to give you 0.63. Are you with me?
Yes, ma'am.
Yes.
Okay, so you're just following the tree diagram and you're saying he's already 0.7, so you follow this route, and then you've got to choose your direction. It's like a maze. You then say it's going to be traffic. So it's 0.7 times 0.9, and we say that is 0.63. Then you're going to say he could also be grumpy if he wakes up and it's not cloudy, right? There's 0.3 chance that he's grumpy, but there's traffic, right? So then you're going to say 0.3 times that. So those are all your possible outcomes. So what I can say to you is from this tree diagram, you can work out certain things. Can you see that? And if you've got to do an or, so I'm going to say, if I say, what is the probability when there's traffic that he's grumpy, right? So you're going to have to say, okay, either it was cloudy and he's grumpy, which we said was 0.63, or it wasn't cloudy and there's traffic, so he's still grumpy, right? So if there's traffic, the probability will be 0.63 or 0.3 times 0.9, which gives you 0.27. And then you're going to add them up, because either he woke up and the weather was nice and there was traffic, or he woke up and the weather was bad and there was traffic. So it's either going to be 0.63 or 0.27. And those are the two opportunities. So you say and, so you add them. Does that make sense? So the two ways it can be is he wakes up and it's cloudy, there's traffic, or so you add the other one. So the answer will be 0.63 plus 0.27, which gives you 3 and 7 is 10, carry 1, 6, 7, 8, 9. So the probability is 90% that this man is grumpy, but he sounds like he's a grumpy fellow anyway. Okay, so let's look and see, because this Mama's maths, I quite like Mama's maths that I showed you just now. I'm going to go back there because she had some nice examples on, tree diagrams, on probability, where we can do the examples. It's easier for me to do this than to draw them and try and show you in this little screen. Tree diagrams. Okay. Did you do your computer projects for Mam Lou?
Yes, ma'am.
Yes.
And you didn't struggle?
Not really.
Not really.
Sorry, but nothing matched your, oh, dearie me. Oh, here, well, here we have some. Okay, so let's go to these. This is not Mama's thing. All right. Okay, so I went to page 8. I'm going to go back to page 1. Can you see the screen that I have here that says bite size?
Yes, ma'am.
Okay.
Yes, ma'am.
So probability, the probability scale is between 0 and 1. We've already looked at that, right? Monday will be the day after Sunday is certain, right? So that's 1. Flipping a head on a coin, you've got an even chance, so it's a half. And picking a blue counter out of a bag that has only red counters is impossible, so the probability will be 0. Right. Then if we look at the second thing they look at, they just explain to you how you can write it as a fraction, right? So or a decimal. Remember, the probability that something will happen is 1 minus the probability that it will not happen, right? So if I had to say to you, there's 11% chance that I will stay at home tomorrow, without me telling you, you should be able to say there's 89% chance that I'll be at school, right? So the two always have to make 1. So on your tree diagram, which is the thing I was showing you just now, this one, where's it gone? Yeah, every single branch, every single V where the branches are, have to add up to 1. All right. So if you looked at that one was 0.7 and 0.3 made 1. This one was 0.9 and 0.1 made 1. So every little set of branches have to add up to 1, and that's very important. So just like if I say to you, if it's a week, what's the probability that it's a weekend? You know it's going to be 2/7, right? You know there are 5 days in a week, so it's 5/7, but you could just have said 7/7 minus 2/7 to get the answer. All right, so that's that. That's very easy. I just want to go through this very quickly because I need to get to the tree diagrams, which is the section I'm doing, which they're struggling with a little bit at school. I had them further on. They do it with percentage. They do it with decimals. You need to be good with the 3. I think you're both okay. I'm hoping you're both okay with that. You see, if a fair die is rolled 300 times, what is the probability that you would roll a 5, right? Well, the probability that you roll a 5 is a 6th, right? And then all you do is you're going to multiply it by 300. So that's not difficult, hey? So if the probability that I get stuck in traffic every day is 75%, if I'm going to go for a whole week, I'm going to multiply that by 5. or by 6 because I've got an open day on Saturday. So whatever the probability is, if it repeats itself, you multiply by the number of repetitions. I think that's easy. Number 5. That's fine. I don't think you have a problem. I'm trying to find my tree diagrams. They were here. Okay, so there we go. So here it says the frequency tree can be used to record and organize information given as frequencies. So they say running club has 160 members, 74 are female, 58 are male. So obviously you're going to separate it like they have, right, over here. Okay. I just want to try something here. My pen is not very visible and I made it much better the other day. Right, so here you see there's the females. And the females are we going to write here 74, right? And then the males will be 58. But then can you see, when they give you the over 18, it's going to be the same. It's not going to be a different number. So the class yesterday were confused and I had to leave them for a visitor at this point. So if they say to you, of the female members, 58 of the female members are over 18 and 21 of the club members are over 18. Complete the frequency table, right? So 58 of the female members are over 18, right? You know that you're going to put it here, right? And you can work out how many of them are male, all right? So 58 females and 74 club members, well, then you can just work out how many males. It's easy, all right? But it will be the same in the one below. That was what was confusing them yesterday because they thought it was a different thing, but it's not. It's only going to give a different answer because of the first part. All right, let's go down. So can you see? Now here, what have they done? What have they done here? Oh, I see what they've done. Okay, wait. They've said 74 of the members are female. 74 members are female. 160 minus 74 is 86. We already knew that. Okay, so you're happy with that one. Am I right? 74, 86 was fine. Then 58 female members are over 18. So 74 minus 58 gives you 16 females are over 18, right?
Yes, ma'am.
16 are under 18. 16, 58 are over 18, 16 are under 18. So what they've done here, they've done it a little bit differently because they haven't said the girls and the boys here, and I understand why. I was being silly. How are you going to have a female that then becomes a male under 18? It won't work. Do you agree? So you couldn't have had females and males here. Okay. So it had to be over 18, under 18. And then with the males, obviously the numbers will be different. So they said with the males, we've worked out that 58 are female, that 65 will be male, and then you've got over 18 or under 18. Does it make sense?
Yes, ma'am.
Yes, ma'am.
Jojo, with you too, okay. So then you have to be able to work out. So if I say to you, you pick a runner in this running club. Say a runner has a fall at the race. What is the probability that this was a female under the age of 18 and we need to call maybe a pediatrician, let's say, right? We wouldn't have to because nowadays pediatricians are only for younger ones. But anyway, so we're running out of time. I'm going to have to just reconnect, hey? So 160 is the total. So the females will be 74 over 160. You agree? So that probability is 74 over 160. But then you can be a female and under 18. When it's and, what do you do, Jojo?
Ma'am, you multiply.
Okay. So times, and then the probability that you're under 18 is going to be 16 over what? So that's 58 plus 16. 8 and 6 is, what is 8 and 6? 14 carry 1, 74, obviously. So that's going to be 16 over 74, right? And that will give you the probability that the person is a female and under 16. Do you agree? So you'll say 74 over 160 times 16 over 74. All right? And that will give you that answer. Now, if I say to you, what is the probability that the runner is under 16? Right? Did they say under 16? Was that over 18? Ugh, I'm talking such nonsense today. I'm not reading. But okay, so over 18. So then you're going to say, what is the probability that it's a female that's over 18? And you'll do that. But then if it's a person that's over 18, you've got to say, or it could be a male that's over 18. Okay. Or under 18,
Yes,
whichever way you want to do it. And then you'll do exactly the same thing on those tree diagram lines, and then you will add them because it's or. You can't be a girl and a boy. You can be a girl or a boy, unless, of course, you're a hermaphrodite. We do have some of those in our country, as we know. Right. Remember what Tumi used to say about those things, my darling? Hey?
Not remember.
You don't remember. He used to always have these arguments with me. All right, so here we have something a little bit different. Okay, so they say two events are independent if the probability of the first event happening has no impact on the probability of the second event. Now, say, for example, we're making party packs. I wanted to make party packs for my birthday, but I didn't. I should have. So we make party packs and we put different sweets inside, and let's say we put Rolos inside. And then Jojo comes in and she's coming to help us, and she says, "Oh, are these Rolos?" And she takes one out of the packet, looks at it and says sees it is a Rolo and puts it back, right? That's not going to affect the outcome. But then Zalo comes and he says, "Oh, I love it. I love Rolos." He takes the Rolo and he eats it. Now it's going to affect the outcome. Do you understand? So sometimes you get outcomes where they'll say you pick a red counter and you replace it. Now the total won't change, so it's independent. But it might be dependent. The first event might have an effect on the second. So we've got to look at the examples of the two of those. So if you look at this one, a sock contains 5 white drawers, 5 white socks. I don't know what's wrong. A sock drawer contains 5 white socks and 4 black socks. A sock is taken at random and put on. Another sock is then taken and put on. What are the probabilities of the different sock pairings? Now, say you're doing this in the dark, you might have funny combinations, right? So they've done a tree diagram. Can you see it? And they said there are 9 socks in the drawer. So there are 5 that are white, 4 that are black. So it's very simple. It's going to be the probability of picking a white one is 5/9. The probability of picking a black one is 4/9. Now, the children yesterday, when we did an example similar to this, wanted to change the 9 in the denominator to 7. And what you have to understand is that you're only looking at one thing at a time. So you can't change it to 7. You need to change it to 8 because you're taking one sock out first. You can't say you're taking them out together. All right. So if the first sock you take is white, then your white socks will go down from 5 to 4 for the second pick. Does that make sense?
Yes, ma'am.
Yes, ma'am.
So, but the total number of socks in the drawer have to be 8. They're not 9 anymore. And then the black socks will remain at 4, but they'll only be 8 in total. So from 5/9, it goes to 4/8. You haven't taken a black one, so it stays at 4/8. If you did not take a white sock, you took a black sock first, the probability of taking a white sock will remain 5, because now there's still 5 white socks, but the socks total number's gone down to 8. And the black ones have gone from 4 to 3 out of 8. If you can understand that, you'll do well, because that's where the children go wrong. They forget to reduce, okay? And sometimes they reduce the number where they've taken one, but they forget to reduce the total. So if they say to you now, so the probability of the different pairings are like this. If you want to know the probability of taking 2 white socks, you're going to say taking a white and a white. So it's 5/9. And 4/8. What do you do if it's and? It's white and white. What do you do if it's and umbiyelo?
You multiply, ma'am.
Multiply, right. So you're going to say 5/9 times 4/8. That gives you the probability. If you're saying the probability of taking a white and a black, you're going to say whatever it is, right? And in the end, you should add all of the probabilities together and they should make a total of 1. Okay. But here they're only looking at 2 white socks, 2 black socks, and 1 white and 1 black. The 1 white and 1 black, there's 2 ways of doing it, so you have to add 2 things together. So you can either take white first and then black, or you can take black first and then white. So you must bear in mind the 2 things. All right, let's see if we move on to test, which I think should only be 1. I hope it's only 1 to do with this. You can try quickly. Okay, someone you know will win the lottery jackpot this week. Which probability best describes this event? What would you say?
Even chance, ma'am.
Impossible, ma'am.
That's what I would say too. Even chance, my darling, is if you've got black and white. You know, if you go to the casino and you're too young to go, so I hope you've never been. But if you play a game of like roulette and you choose positive numbers or odd numbers, you've got 50% chance of winning. But winning the lotto is not 50%. It's like a 1 in multi-million because there's so many different options. Okay. So it has to be very small. So it would be very unlikely, probably, Jojo, not impossible, right? But very, very, very unlikely. Which of the following is not a measure of probability? An improper fraction, a decimal, or a percentage?
Improper fraction.
Good, because remember it has to be less than 1. Good boy. Right. The probability of Paul being late for work is 0.55. What is the probability that he will not be late for work?
Ma'am, it's 0.44.
0.45. Are you with us, Jojo?
Yes, ma'am.
Okay. What is the probability of selecting a vowel from the word mathematics?
Ma'am, it's 4 over 11.
4 over 11. Jojo, are you with us? Isn't BL or being too quick?
Yes, ma'am. I was still counting, ma'am.
Okay. A fair dice is rolled 120 times.